When you are working with exponential problems, sometimes it may behoove you to change the base. And this happens often when you're talking about cells that are replicating. So like if they're doubling when you do go through natural mitosis in cellular division, or if it triples, like if it's a bacteria. So your base, if it's doubling, would be 2. If your base is tripling, would be 3. This can sometimes be problematic because you don't have base 2 or base 3 logarithms that you can work with regularly, but we do have base e that we can work with quite easily. So there is a way to change from any base to base e, and this is how you do it. Okay, so if you have this exponential problem where b is any base, it could be 2, it could be 3, it could be anything. What you can do is you can rewrite it like this. Notice the a is the same, right? So your initial amount is still the same. But then the b, so the b becomes this right here, e to the natural log of b. And if you remember correctly from all those exponential rules we talked about and logarithmic rules we talked about, if you have a base e and a base in your logarithm of e, they kind of get rid of each other and you're left with b. So that's where that comes from. So we can take any base we have and change it to a base e at any time, which personally I'm a big fan of. So say you have this problem. Y equals 4 to the 7.8 to the t power. I would like you to rewrite it with a base of e. All right. It says express the answer in terms of a natural log first, and then round any decimals. Okay, so we're going to rewrite y. We're going to keep the 4. And instead of 7.8, we're going to put e, natural log of 7.8. And then we're going to multiply that by a t. So that is leaving it in terms of a natural log. Okay, then I would get my calculator out and I would find out what the natural log of 7.8 is. And again, this is going to give me approximation. It's not going to be equal. We should be good. We should not write equal. We should write approximately because it's not going to be exactly. This is going to be e to the about 2.05. They said 3 decimal places. Yes, 54 t. So I just put this in my calculator and I got this. So there is these two are almost identical. They are approximately, they're very, very close. So if I were to graph both the original equation here in my graphing utility, and then when I was to graph this one, they would be extremely close to each other, if not almost identical. And if you don't believe me, please feel free to go out and check that out on Desmos. Put in both of those and see what happens. All right, so let's actually put this to some use. When am I going to actually use this? So say that you have found an aggressive bacteria, and this bacteria triples in number every 30 minutes. So let's say you put 90 bacteria in a petri dish, right? Part A, I want you to write an expression that models the size of the population after t hours. And then part B, how many bacteria are going to be in that petri dish after 4 hours? All right, so let's start with part A. All right, so these can also be modeled using a very similar to our exponential growth and decay. So our final amount is equal to the initial amount times our base raised to the time t. Okay, so we don't know how much is left, the initial amount, so I'm going to leave a here. But a sub 0, I know. I started with 90 bacteria. So my a sub 0 is 9. My base is 3 because it's tripling, right? If we're tripling, so that means my base is going to be 3. And notice it says the base, that bacteria triples every 30 minutes, which means it's going to be twice an hour, right? Twice in every hour. And remember, t is always time in hours. Okay, and again, it even said that t is time in hours. So twice an hour, this bacteria is going to triple. All right, so if we clean this up, you can leave it like this. You could write it like this, 90 times 9 to the t, because 3 squared is 9. So that would also be another way you could write it. But notice that both of those have a base 3 or a base 9, and I don't have any of those on my calculator. So what I would do is I would write this as base e. Okay, so this is going to be e, a is going to be approximately, and again, remember we have to put the approximate because we're going to have to round some stuff. So this is going to be 90 times the natural log, wait, helps if I write my e first. This is going to be e to the natural log of 9 times t. And the natural log of 9 is approximately 2.197 t. So that is the equation that would approximate this population um, for time t. So any number of hours, we could just plug it in and be done. All right, so part B says let's do that. So how many bacteria will there be after 4 hours? So my final amount will be approximately 90 times e to the 2.197 times 4. So I'm going to put that all in my calculator, and my A is going to be approximately 589,959.8 bacteria. Okay, that's a lot of bacteria. I don't even want to think about that now. Okay, and if you want to be sure that it's actually a good approximation, go back to your original. So if I take my A equals 90 times 9 to the t power, and I plug in 4 for t instead, and plug that into my calculator, I get 590, 490 bacteria. So that's a pretty good approximation, right? Look at how close those two numbers are. Pretty dang close. Okay, so this is a good approximation for the original. So you can always change your base if you would like to from any base that you have, like a 9 or a 3 or a 2, whatever it is, and change it to base E, which I think is just a little bit more user-friendly. But again, remember, it's not going to be perfect. It is going to be an approximation because you are going to have to round that natural log, right? That natural log, we had to round it to a couple decimal places. The more decimal places you use, the more accurate it will be. All right, so hopefully that helps. Go practice, and I will see you next time.